All right, grasshoppers. I haven't done this since last track season, so doing my best to make sure you guys are getting the thinking process and not just the right answers, but hearing how. So, bell ringer 1 should have been done already. Answers over on the board. Yesterday we introduced that fourth trend and started to really practice it. So, if you haven't tried this video, you shouldn't do it, but or watch this. Make sure we've given it a good try, but otherwise, feel free to grab red pens and let's rock and roll. So, remember, on our multiple choice questions, we need to make sure we're thinking about what answer we want before we go find it. So, number 1 says the bromine ion. So, everyone, bromine we know wants to be -1. I don't have to tell you that. You should know that's the ion. Is larger than the bromine atom because. So, right away, if we go think about, okay, well, bromine is 5p5. If it gains 1, it's 5p6. So that doesn't really help us understand why it's larger because 5p6 and 5p5 are basically the same thing. We have to make sure the electrons don't tell us a story. Go to the protons. Well, we have bromine both times here. Let's see if I can make this a little bigger. We have bromine both times here, but now we've all of a sudden gained one more. So that's that whole idea of if I'm walking 35 dogs and now they add another one, those negatives are going to push each other apart even more. So we'll have more repulsions and a bigger cloud. That's why it's bigger. So that's letter B. Letter A isn't true because they have the same positive charge because they're both bromine. Letter C is wrong because it doesn't have a fewer electron. It has more electrons. And then the last one doesn't make it has a full valence shell, not an empty valence shell. So number 1 should be B. Number 2 is a real high level one that you'd have to probably take a few minutes and think about. But I've told you guys, kids will think that all of these things are isoelectronic, and then everyone says they're exactly the same size, which is wrong. That's what this absent kid did, and hopefully you did more than just say it's wrong. Hopefully you went and did what was right. So going through our steps, as always, we want to start with electron configuration. So bromine, that's a -1. Remember, if there's no number, it's 1. Normally 5p5, but if it gains 1, it's 5p6. Normally strontium is +2, so that should say 6s2. Whoops. It loses both of those. Now it looks like 5p6, which is that noble gas. Rubidium, normally 6s1, but it loses it, so it's 5p6. I think I don't have that noble gas in front of me, but selenium is normally 5p4, but if it gains 2, now it's 5p6. So all of these things are indeed isoelectronic. That kid is not wrong, but we need to remember, are they similar size-wise? Yes, but if those electrons don't really tell us what we need to know, we need to go and look at the other part of that atom and its size being pulled, so we'll go look at the protons. So if we go to look at those protons, we got to make sure we go, and I'm 35 pulling on 36. Strontium has 38 pulling on 36. Rubidium has 37 pulling on 36. And selenium has 34 pulling on 36. Again, 36 electrons, showing again that they're all isoelectronic. So as far as the ranking now, I just always start with an extreme. If we go look at all of these, 38 is by far and away the most positive, which means it's going to pull the hardest, which means strontium +2 is going to be the smallest. I always start with the extremes, and you can go whichever way you want, but that's what I always do. So then, again, building on the extremes, out of everything that's left, 34, a 34 versus a 37, that person's ugly for sure. Not really in real life, but just meaning that those 34 positives aren't going to pull as hard. So they're not going to pull as hard, which means selenium -2 is the biggest. And then again, we have those other two left. If we look at 37, that's going to pull a little bit harder. So rubidium pulling a little bit harder would be smaller than bromine. And just remember, when you look at all this, this makes sense. When you lose electrons or lose weight, you get smaller. When you gain electrons or gain weight, you get bigger. So that's only that idea, though, if you're really comparing them to be isoelectronic. So big thing here is just make sure we're building the habits of making sure our numbers are and our evidence are supporting our answers, not just magically getting it right. Okay? So, other ones. Ionization energy is the energy it takes to steal an electron. So just don't get caught up by the language. Just keep working on which one would I want to steal from. So number 3, which one has a larger IE? That means harder to steal from. Things that are hard to steal from, like I put up here, are noble gases, or things like noble gases. So if we go look at magnesium or oxygen, magnesium is 3s2, oxygen is 2s2, 2p4. So magnesium has 2 valence electrons. Oxygen has 6 valence electrons. Which one would be harder to steal from? Easily, oxygen. That has 6 of the 8 princesses. It's going to be hard to steal from. It's much closer to being a noble gas. Magnesium doesn't even really want those 2, so that wouldn't take very much energy to steal from. Keep using your electron configurations to help you get the answer. Okay. Number 4, which one is harder to steal from? So we have fluorine, which is 2s2, 2p5, or neon, which is 2s2, 2p6. Now, both of these would be very hard to steal from, but there is a minute difference. I mean, fluorine has 7 valence electrons, whereas neon has 8. You're going to have to work hard to steal from both of these, but neon is much more stable as a noble gas, and it would be harder to steal from. I mean, it'd take more energy and have a larger ionization energy value. Okay, the last one. Which one has a larger ionization energy? Harder to steal from. Argon and neon are both noble gases. So we see those full octets. They're both very hard to steal from. So now this is that other trend going up and down. Both of these have 8 valence electrons. They're both very stable. They're both very hard to steal from. So what we have to think about now is that shielding. So if I have 2s versus 3s, that whole idea, that 3s is going to have more stuff in the way, whereas that 2s, those are still really close to the homecoming queen. So that's that whole idea, and we need to get good at using this verb, but neon being smaller has less stuff in the way and less shielding. Less shielding means those kids are closer to that queen, and you're going to have to work really hard to steal those ones. So neon being smaller with less shielding would be harder to steal from than argon if you compared the two directly. Number 6, I kind of did with you guys yesterday. I know a couple of you were gone, but you should have here. Easiest to steal from is very, very big, and it'd be from the first column. With all that shielding, that'd be francium. I know I didn't really do this one due diligence, but I talked about it yesterday. Just make sure we're thinking about those families, and if it's easy to steal from, it's probably an alkali metal. If it's hard to steal from, it's a noble gas or something like it. Okay. Backside, number 7. Speaking of that, what is the name of the first family? That is the alkali metals. Remember on page 4 and 5, I expect you guys to be doing some of that notes on the families. It said what we know about those, and I'll go through this next week, but alkali metals, that's one word. Alkaline earth metals is 2 words. That's group 2. So those all have 1 valence electron, and if it says it's medium ionization energy, we'll have some problems where you have to like kind of do a puzzle to figure out what it is. But if it's medium, we know the top of the family is very hard to steal from because they're close. The further down you get, the more shielding you have, the easier it is to steal from. So medium would mean it's not at the top or bottom. We're probably looking at something in the middle here, so probably sodium or potassium or rubidium. 3s, 4s, 5s. Those aren't going to be really easy to steal from at the bottom, but they're also not going to be hard to steal from at the top. They'd be medium. Number 8, make sure, and I think I wrote this, know what you're looking for before you go. So it says, which electron configuration would have the lowest ionization energy? That would mean it's easy. It doesn't take very much energy to steal from, so it's easy to steal from. Something that's easy to steal from is not a noble gas. Noble gases are hard to steal from. So really what we're thinking about here with a low IE, it probably only has 1 or 2 valence electrons because it's easy to steal those. If you go look, letter D has 7 valence electrons, very hard to steal from. Letter C has 5 valence electrons, hard to steal from. Letter B has 4 valence electrons, yeah, but by far and away, A, that'd be like lithium. It'd be easy to steal from lithium. It doesn't want 1 valence electron. So that's just that whole idea of not getting caught up by, tricks and questions. Know what you're looking for, and that's the whole pattern we got to know, okay? Number 9, a horizontal row of blocks. Remember, these are columns, but we'll say groups and families. These are rows, and what we'll kind of talk about later is that those are periods where they kind of repeat themselves with those patterns. Okay, and last but not least, I'm going to guess half of you didn't try number 10. Probably a couple of you didn't try number 10, but kids will go, nuclear charge, what's that? Well, if we think about the nucleus, what charge is the nucleus? Positive, because of protons. So all this question is really asking you is which one's more positive? If calcium has 20 protons and selenium has 34 protons, which one's more positive? So selenium definitely has a greater nuclear charge, and we know that that's important when it starts to talk about pulling on those electrons. Between the size here, this is 4s, this is 4p, but 34, that greater nuclear charge is going to pull harder, which is why it gets smaller as you add more protons across a row. So those can go in the basket. I'll keep them. Answer key to bell ringer 1's over on the board. I put the answer keys to the assignments over on the far board by the north side there. I starred those pages in your packet. You need to be practicing. Don't forget page 4 and 5 and those notes over the families and metals and non-metals that you need to do. Let's plan on, I'll kind of leave it up to where you guys are at, but probably sometime between maybe 10 to 30-ish maybe. Let's plan on clearing everything and taking a break, and then I need to put some pressure on you as far as you feeling how to do this. So that'll be Trends Quiz 1. I'd say, I don't know if I put it on my sub notes, but you'll try it on your own for, let's say, 10, 12 minutes, and then I'm fine with you partnering up, but no big groups of 8 in the back with one person doing all the work. And if you guys need me to put stuff on Canvas or you can't find stuff, you can take pictures of keys with your phone and stuff. I don't think I updated Canvas before I left school, but use your class time wisely and make sure we're on top of things. And I'll be back to review on Monday with you, but we need to keep plugging along in this unit and making sure we're practicing. So behave, be productive, and I'll see y'all later.